start the recording. So welcome everyone. Today we're having our speaker event by Professor Luca de Alfaro. He is a distinguished professor who does a lot in fairness and AI, and you can take it away.
Thank you very much. Yes, I'm actually not distinguished professor. It's an official title and I'm not distinguished, but I'm happy to be at UCSC nevertheless. So what I want to talk about, let me share the screen a moment, is a few topics that I, wait, is the screen sharing working? Sorry, let me
We
just...
could see the Google Slides, but not in presenter mode.
Yes, but that would be what I wanted to have. It's just that I lost the confirmation that I'm sharing. Okay, fine. I hope it will work. Good. So I've been doing various things. If I go back some 10 years of my work, right? I was working in reputation systems, so then I did a little bit of work on fake news, then a bit of work on AI, then a bit of work on this and that. And now I'm sort of reorganizing my thoughts about what is of interest to me. And I realize that most of the things that interest me in this moment are something that I call computational ecology, which doesn't necessarily relate to the natural world, but it relates to essentially this nexus of interacting objects that can interact and learn from the interaction and maybe behave or change their behavior. That's a sort of the common thread of the talk. And I'm going to present to you three things that I'm doing, each one of which has a beginning that has been done and some future directions that are open for future work, essentially. Stuff that I would like to do in the future with either graduate or undergraduate students, but things that I think would be of interest for the future. One of my main defects as a faculty member is that I'm very easily bored of what I've done already. And so all my energy is always in what I haven't yet done or I don't know already. And I think some of these will be reflected in this talk. You know, there will be some information about what's there already, but also a lot of, tendency to go forward to the future, sort of, where I haven't been yet. And I'm going to talk about three things in particular. So learning to take turns. So how is it possible to learn how to take turns? Why is it an interesting problem? How can we do it in a way that is useful? It turns out that it has important application to networks. Then I want to talk about some work I've been doing about finding anomalous subgroups in data. When you build a machine learning system or a classifier or one of these, or even when you look at data that is pre-existing, for example, university admission data or any other data set, you may be wondering, what are the groups of people, if the data set is about people or of input data that behaves in a different way or is treated in a different way. And so that's work that I want to mention. And the third topic, it will be mentioned in a briefer way because I don't have papers yet on that. We are trying to publish in the near term, is about applications to the study of bird habitats. So these are the three topics. I'm doing a small amount of other things on the side, such as a mix of these game theory and learning to take turns to study how behaviors can arise in human or animal populations. But that's also work that is still going on, and I decided not to present it at all. But maybe next year we'll be ready. So let's start with these. Actually, no, let's start with me trying to bring up the chat. Yes, so I can see if anybody asks questions, I can keep an eye, or you can raise the hand. Cohen, if you can look at questions on the chat and on the raised hands, that would be helpful. Okay,
I'll let you know.
Okay, thank you. Yeah, so I can just focus on the talk. So let me go back to it. So learning to take turns. This is joint work that I did here at UCSC with JJ Garcia Luna Seves, who is a professor here in our department, a great expert on networks. and the department chair. I'm the co-chair. We liked so much working on this topic that we decided to be chair and co-chair together. Not actually a joke. And Molly Zhang, who is a PhD student, actually was a PhD student. She happily graduated 1 year ago. And so this is what we did. So we want to learn how to take turns. And why is this interesting? Because there are some mediums in which there can be only one person that talks at the same time. I mean, I don't know if you have ever wondered how information is transmitted, but one of the simplest ways is to have a frequency, or maybe a fiber optics or a cable, and to inject communication into it. And if one sender is talking at the same time of another, the communication is garbled. So users, in this case, they have to learn how to take turns. So if user one talks, the channel, which is a shared communication medium, maybe the radio waves, contains what user one said. If user two talks, then this works as well. But if two people talk during overlapping intervals of time, then there is a collision, okay? And so one of the oldest network protocols, really, it was called the Aloha protocol. It was developed in Hawaii. Some people put a mast on top of well, not really on top, but close to the top of a volcano that contained a retransmitter, okay? And all across the islands, people could transmit a packet of information, and if the transmission went through, fine, and if there was a collision, there was a specified delay with which they would try again to retransmit, okay? And this is very important, this type of protocols, because these are the protocols that can be used to start communication when no prior agreement exists. Many actually more modern protocols use Aloha as a component in order to get started, and maybe then the people via Aloha communicate, perhaps a more sophisticated scheme and then transition to the other one. But to this day, Aloha is quite important. And by the way, the wireless communication that you use via your Wi-Fi is essentially on a modified version of this protocol. So the basic idea of taking turns is very much used all over the place even now. And so if you just do something as simple as that, the max utilization you get, if you do an optimal retransmission policy, you can do the calculation. It's actually beautiful that you can do it analytically, but it ends up being about 18%. So 18% of the time can be used in useful transmission. All the rest is lost to either empty time, where nobody is transmitting, or collisions, and so things that need to be retransmitted again, okay? So this is not so great. And so first, a simple improvement was to, you see these two packets, the red and the green one, collide because they partially overlap. And it seems silly to allow partial overlaps, right? You should either not overlap, or at least if you really need to collide, you collide seriously. I mean, this is not applied to traffic, obviously. But to packets, that seems to be, it just multiplies the possibilities in which people can step on each other's feet if they even colliding by a small amount is bad, right? So the obvious next idea was to create time slots and say that you transmit in a time slot. In this way, either you completely collide or you don't. And if you do the calculation, because this roughly, not roughly, precisely halves the probability of collision, because now you have to be fully in the same slot, the maximum utilization goes to 37%, which again is not great, right? You would like to be able to do something smart and learn when you can talk so that the other people can talk as well, and carry that on. And so this is a problem. Can nodes learn how to coordinate? And so one idea is to use reinforcement learning. And because people sprinkle AI on top of everything, even if they don't know necessarily how good it is, some people tried, not me, right? So they did reinforcement learning for choosing the transmission slot. This was a paper from 2012. And what they did is this: they considered a fixed length of slots, okay? And they said, okay, let's learn via reinforcement learning which slots are good to use and which ones are not so great to use. So they associated a quality with each slot, and they wanted to learn the quality from observations, okay? And so the idea is that every sender would pick the slot with the highest quality and use that in order to send. So if you have 3 senders, right, you would pick, every one of them would pick the slot in which their notion of quality was the greatest and the transmit. What does it mean the notion of quality was greatest? Well, you keep this floating point number for every slot that says how good it is. And if the transmission goes through, you increase it. And if the transmission does not go through, you decrease it, right? And so they had a simple rule, a non-neural network involved, but they had this sort of adaptive rule in which they were learning these. So if you want, the reinforcement learning was used in a simple way, but actually some of the MAVT faculty members actually from this department laid the foundations for these type of learning between finite number of alternatives. Unfortunately, they are all retired now, but David Hembold and Manfred Warmuth did a lot of the foundational work. It was a very great work that is used, widely in practice. And so these people essentially chose something simpler. Unfortunately, they didn't read the papers of Manfred Warmuth closely enough, so they didn't quite implement it in the best way. But that was their proposal to use reinforcement learning. And there are 2 problems. One is that the frame is fixed length. And so, if the frame is of length 40, if there are only 5 senders, so the max you can get is 5 out of 40. Is not very good, right? That's one of the problems. And the other problem is that the learning is very slow. There is nothing really that drives the learning rather than a trial and error. And the point is that in many settings in machine learning, and this is a theme in many things that involve networking, we have used to see this setting for machine learning that is basically offline. We get a bunch of data, we study the bunch of data, and once we are happy with a bunch of data and our model, then we publish the paper, or maybe we actually use the model if we are not in academia. But in networks and in many other applications, so that doesn't quite work, right? Because you want to learn fast while what you learn is still going to be useful. It would be quite useless if you have information to transmit, to spend a lot of your time learning and, imagining what your strategy should be. And, and your data is not being sent, it would not be a good way to have a Zoom call if my laptop was trying all the time to learn how to communicate with the people, I guess. Okay, so slow learning is really an issue in these dynamic settings. So what we did is we introduced, actually somebody proposed it in another context before, but so we resuscitated this idea of a policy tree. We essentially wanted something that can help resolve conflict. So the idea of the policy tree is this. These nodes say when you can transmit. So a node is labeled by IM, and you can transmit at time t if t mod 2 to the m is equal to I. So this is the reminder. Okay, let me go in this way. This is division by 1. If the node would transmit all the time. This node transmits when the modulo 2 by 2 to the 1, so the modulo 2 is equal to 1. So this transmits in the odd slots, okay? This node transmits when the modulo with respect to 2 to the 2 is, so far, is 1. So, this would pick one of the 4 slots. So the idea is this: if you go from a parent to a child, you transmit in half of the slots of the parent. Okay, every time you go down one level in the tree, you are picking half of the slots of the parent. And the union of the slots of the child is equal to the slots of the parent. Okay, there is another part to this idea that I hope I do in the next slide. Yes, that is 2 nodes that are not one the ancestor of the other do not have any conflict. Okay, because they, these and this node do not have any conflict, and this child is a subset of the parent, so there is no conflict there. And so this tree is useful for a bunch of reasons. One of the reasons we created it is this. We knew that if you don't know how much information you need to transmit in a network, a very good general idea that has worked well throughout the years is to say, when you transmit too much, half the amount, divide the amount by 2, so that you quickly reduce what you're doing and you don't congest the network. And doing it here would be simply amount to picking a child instead of the parent, right? So there was some properties that by nose seemed to be good. And then there is another important property, that is, if you take a tree of this size, imagine that you have a tree of depth m. You have and you pick one of these nodes, okay? You are going to have m conflicts. So sorry, let me do it this way. You have a tree, you pick a node, and then somebody else picks a node at random. What happens? Once I made my choice, there are only actually m minus 1 other nodes that will conflict with my choice. No m, because the other person can also choose what I chose. So there are m choices for the adversary that are conflicts, but there are 2 to the m minus m total other nodes. So this means that if I and Cohen, independently pick 2 nodes, the probability that we have a conflict is low. So this tree intrinsically tries to reduce the conflict. Okay. If your strategy is, if there is a conflict, I will go down 1 level in the tree somewhere, even at random, in general, you will do well. And so the idea is, can we take this policy tree and make it go better with learning? Okay. So what we did is simple. We associated a quality with each node. And then we decided we associated a quality with every node of the policy tree. And every transmitter would transmit according to the node that had the highest quality, and also other nodes that have high quality. So you always pick one because we don't want anybody to be totally silent. But if you have multiple nodes that all have high quality, you can use them all. Otherwise, we would be very constraining your policy to have a throughput that is a power of 2, essentially. And we don't want to do that, okay? So this was a very simple idea. Now, I'm sparing you a lot of the non-interesting. It depends on how interested you are in networking. But there is a lot of detail and a lot of work that we did on these. So we published several papers because these network protocols, then you need to look at the detail. For example, how do I know that I had a collision? Can I detect a collision when I send the packet because I listen to what happens if somebody else is talking at the same time? Do I need to be told by the receiver that they didn't receive it? Can I be told by third parties? How is the notification happening? So there is a lot of detail that I'm essentially sweeping under the carpet, right? But this was a general idea. So a reinforcement learning that was quite trivial because it needed to be quite fast, and that it used this idea of a policy tree to essentially drive the learning, okay? This is what we did. So this slide, I mentioned it already. Yep. And so these are some of the results. So Aloha Qt and QTF are our versions of the protocol. The F stands for fairness. I can tell you by voice what this implies, but the problem is this. Suppose there is only me and Cohen that talk over the network. So sorry, Cohen, I use you as the prop, okay? But there is me and Cohen, and so what do? After a while, we probably figure out that a good way is for me to transmit in the odd slots and Cohen in the even ones, and we are very happy. But if we do this, it becomes a problem for other people to enter, to start the conversation. And, we want to make sure that if there is Luca and Cohen and Jonathan, the next one in my list of people here in the call, if Jonathan also wants to barge in, eventually Jonathan, and eventually means also quickly, Jonathan has to be able to command about 1/3 of the total bandwidth. That is, we need not only to be efficient, but we need to be fair and we need to be responsive to changes in the user needs. So we have two versions of the protocol. One is called Aloha Qt, that is a little bit simpler. And the other one is called the Aloha QTF, that has some mechanism by which the nodes observe how much bandwidth is being used and spontaneously relinquish resources that they have in order to ensure that there is a certain percentage of the network time that is free, so that other nodes can more easily start and gain the right bandwidth. Let me put it. Let me do a comparison in a very different setting. Imagine you are in the feudal times in France before the French Revolution. So there are these people with a castle that own all the land, and you own nothing, right? And this is not a very fair system. It wasn't very fair then, and it wasn't very fair in a network. In the network equivalent, Luca commands all the top nodes, and everybody else is left with the crumbs. And reinforcement learning per se does not ensure fairness if you are not a little bit careful. So what we did is a sort of law that says that every year, with a small probability, you roll the dice and you lose your castle if there aren't enough free castles. We want at least 5% of France castles to be empty. Okay, and so we command all the castle owners, to roll the dice, and if you're unlucky, you just quit your castle, so that people who need a castle, eventually will be able to rotate in. And this is a bit of a joke with the castle, but it's exactly what we did with the nodes. So essentially, there is a rule that says that if you are holding a node and you're using for transmission, if the percentage of free time in the network goes too low, randomly you flip a coin and you decided that you relinquish your node and you go to one of the children instead. So we have rules of that type. And so Aloha QTF is the fair version of the protocol. And so you see, if we throw 50 nodes at once, our utilization goes to very high, 80% or more, fairly quickly. This is the number of time slots. So, if you're happy here, it would be 500 time slots to make 50 nodes learn how to take turns fairly efficiently. So this means a node transmits basically 10 times. And by the 10th transmission and a lot of listening, it has figured out when to transmit. This was quite fast adaptation. We thought it was a nice result. If you look at what happens so here is an example in which you go from 20 nodes to 50 nodes, back down to 30 nodes, and you see that Aloha QTF, Aloha Qt doesn't work so well for fairness, so we didn't show it. But Aloha QTF, which is as, works quite well. So we go up, then when people go missing, from the transmission, initially the utilization goes down, but then the nodes discover that there is extra space in the network to transmit, there is extra free slots, and start using them. And the fairness, this is our algorithm. The fairness, if it's 1, is perfect fairness, and it's actually not too bad. Okay, so there is this drop at some point, but it's not it's not a drastic drop. The other protocols are quite fair. They're just less efficient because they never learn on time. You see, Aloha Q always stays at low level of bandwidth because it can never learn enough. And Aloha EB is the classical Aloha that doesn't even try to learn. If there is a collision, they retransmit after some time. They work extremely well in a stable way, but they just waste a lot of the bandwidth on the network. Okay. So this was basically what we did, and we did it in multiple sources that I spare you because there were multiple versions of these networks, depending on how you figure out that a packet is lost to a collision, depending on how you get information about what the other people are doing. So there are various scenarios for these, and where do we go from here? So virtual time slots is again something that is interesting to network people, but I spare you. Another thing that I'm really curious is what about okay, I want to explain it without reference to the slides because I want to explain it in a different way, perhaps. But we want to essentially ask two general questions. One is, here we did it with
Looks like he disconnected, so we'll give him a bit to come back.
I think I should be back on, right?
Yep, that's your back.
Okay. So I wanted to tell you, we're looking at various things. One is we solved this with a hack of this policy tree. Could we solve it in a better way by framing it as a more general reinforcement learning problem with an appropriate reward function? And this is a problem that somebody interested in reinforcement learning could actually tackle if any one of you is interested. You know, there would be a way to frame not only the fact that you have to transmit your data, but also that you have to do so fairly and study more general approaches to these. So, you know, forget about networks. Imagine that there are n people that need to learn how to coordinate. What are the best loss functions that we can use in order to drive both fast agreement and fairness in the division of the resource? Okay. And I have some ideas on these, and I really would like to test it. So, this is also in part connected to game theory. I don't know, probably few of you know game theory, but let me tell you this notion from game theory. When imagine that I play poker with Cohen again, right? And so I have my own complicated strategy in order to bluff or not to bluff, etc., etc. Or maybe we are this works better in a cooperation game. Like Luca and Cohen need to go to the movies together. But they need to choose their probability every day. They cannot go every day, it would be too expensive. And so they need to choose their probabilities for going to the movies, and it's hard to do, right? And game theory has this notion that it appeared absurd to me for a long time until I finally understood it, which is called a coordinated equilibrium. A coordinated equilibrium means that there is something that both Cohen and I can look at. It has no influence on the outcome of our game at all, but by its simple existence, it can make it easier for the two of us, for the players, to achieve a strategy with higher reward. And when I first read about that, I thought, this is bullshit, you know? I mean, it's impossible. If the thing that has no influence on the game, why would its simple existence? It sounds almost as the way you justify religion, right? Well, it has no influence on the world, but it exists and the world is better, right? It's similar to that argument, but this was a mathematical argument. And then I realized how it works. If it's Cohen and I trying to go to the movies, the external thing could perhaps be the day of the week. Very quickly, we could find out that if we, instead of randomizing every day, if we had a strategy, you know, by the simple existence of the calendar, I observe that I go to the movies with him more often when it's Friday, and, you know, he can make the same observation, and pretty soon we might converge on a strategy that calls for going to the movies on Fridays, coordinated together, right? So the existence of outside information is helpful, even if the information has no bearings on the outcome of a single gameplay, simply because you can look at it. And so it seems to me that we could justify the use of the policy tree in the same way. It's a sort of external clock that everybody in the game can look at. It has no influence on the existence or not of collisions, but it helps people coordinate their decisions. And so I wanted to actually test this hypothesis, if anybody's interested, to try to set this up, this coordination problem as purely reinforcement learning. and try to see whether the existence of an external frame of reference will make it faster to converge. And I think this is an interesting question in general. There is a lot of work on reinforcement learning, and everybody tries to converge fast, of course. What are the things that if you could look at would help your convergence, even though they have nothing to do with the actual problem? No, that's a kind of acute question that goes through my mind. Okay, end of one topic. Now let me go to the next topic. The next topic is finding anomalous data subgroups, perhaps closer to what you're interested in normally. So this is joint work with Elena Baralis and Eliana Pastor from Politecnico di Torino. Elena and I were colleagues long time ago during our studies in Italy, and Eliana is now Elena's student. Elena is a professor there. So imagine you have a bunch of people or of entries, and you have a certain performance for your classifier of your whatever method, right? Okay, fine. But you want to be able to find groups of people for which you may have a higher error rate or a lower error rate, right? Imagine that you do a classifier that tries to predict, for example, student success in their first year. Okay, this is not actually a joke. The university has such a classifier, and we use it we use it in student admission as one of the many things we use. Actually, it's not the major thing we use. It's a very minor one, but we have it, and so you may wonder, who are the people from whom we get it wrong, right? Is a legitimate question. Is it going to be, I don't know, the people that did these studies, or did those other studies? Is it going to be more this or that ethnic group? Do we get it wrong more often for males or females? Who knows, right? And so we may be interested in knowing, actually. Okay, this is a very common problem. Suppose you do an image classifier. You have a bunch of images, and after a while you want to know, for which kind of images do I get it wrong more often? Is there a way to group them and figure out which groups? Okay, so that was the problem we started with. And so there are various reasons that this question is interesting. One is model validation. That is, we want to know whether the model works well. If you just look at the overall performance, you may get the impression that the model works well, but in fact, there may be some groups of data that may be relevant for you where the error rate is very high. Think at the face recognition for skin colors that are darker. Okay, this was a problem for some companies some time ago, right? So they thought, oh, okay, we get a really good performance for the face recognition, and then it would go lower for some people. Speech recognition. For example, my accent, doesn't fare so well. Italo-Americans like me that haven't shed their accent, the best way for me to have my English recognized by Google Voice is actually to pitch my nose, and it's not a joke. And I used to infuriate my friends who work on voice recognition. Okay, so there are, you may want to know, for example, that there are accents in the US or groups of people or ethnicities that don't do as well compared to the general average, right? Error analysis, fairness, if these decisions have implications as in admissions or as even access to technology, such as speech recognition, you get into fairness, right? Issues, right? Is this group cut out from technology? For example, if you have two groups, one can make it through the phone screen easily, and the other group to which I belong is always stamped by these automated voice recognition menus, then at some point there are fairness issues. And also model understanding is an issue. So we decided to start looking at data sets in which we have attributes. Think at it as a pandas data frame, essentially. You have columns, right? So you have attributes, and we can slice the data set based on attribute value pairs. You can slice according to age, according to income, and then you would get this subset, right? So you see here is slightly more red, the data set, right? So we want to find essentially which kind of slices have behavior that is different from all the rest. That is how we frame the problem. And so we wanted to explore all the data subgroups, all the slices essentially that have an adequate representation in the data set. We don't want to waste our time with, I don't know, men over 200 years old that reside in Louisiana, you know, because it's an empty set. So even though you can slice age in arbitrary ways, we wanted to focus only on groups that have a certain minimum size, with the idea that the smaller ones are either statistically irrelevant or, you know, or empty. Okay. So we built a tool and all the theory behind it, and I'm going to tell you a little bit about it. So we surprisingly actually introduced this simple notion of divergence. The divergence of a subgroup, here is called pattern, because data mining people already invented the idea of these slices, right? So this pattern is this, for example, age between 20 and 35, income between 30 and 40K. No, this is called a pattern. And each one of these, age is equal to 20 to 35, each one of these is called an item. So we take many items and we form a pattern. This is what people in data mining have been doing, right? For some time. So if a pattern identifies a subset of your data, of course, and we defined this notion of divergence, which is simply the average of a function over the item versus the average over the whole data set. Okay, so for example, you can ask, for all the people between 20 and 35 that have this income range, does the model have more false positives than for the general population or not? Imagine you're gonna give loans to people and you wanna analyze the false positive probability of predicting a default, right? So the people for whom you are skeptical that they will be able to repay. You want to find out who are the patterns, who are the people that for which I have a highest probability of without cause, of erroneously predicting a default, right? You don't want to discover that that's a minority, right? Because that would be bad for fairness, obviously. Okay, so are you with me up to now? Yes, I don't see any question, but I think, sorry, let me bring it up again. Okay, so okay. So this is an example. So we looked at, like many people do initially, at this Compass dataset. This Compass dataset had the defendants' data, criminal defendants' data in it. And then it tried to predict based on this data the probability that they would recidivate, that is, commit another crime. And this was used in order to make bail decisions. If it was very likely that you would recidivate, they would deny your bail, or your parole, actually. And if it was unlikely that you would recidivate, they would grant parole to you, and so that you would be able to, I don't know, go out under controlled release, right? Something like that. And this has a big significance from a fairness point of view, because if you are going to predict that, say, all the Black people are more likely to recidivate, even though they are not, then that's a way to keep them incarcerated, obviously. So this is very, it has obvious importance for fairness. And so we wanted to find what are the subgroups that had the biggest delta in the false positive rate. These are the people who are going to be disadvantaged, right? Because you predict that they're going to recidivate, but they don't. So they are going to essentially unfairly keep them in jail, okay? And so the beauty of the approach is that we can just feed the data set together with the truth the ground truth to our tool. And this tool will slice and analyze all the various patterns, all the various subgroups that arise, and find the ones that are most problematic, okay? And in this case, it was age between 25 and 45, prior crimes greater than 3, race is equal to African American, and sex is equal to male. Okay, so young black men who committed over three prior crimes. Okay, and so this is the output of the tool. It tells you how divergent is the group. This has a 0.22 over the false positive rate as a general population. It tells you the subpart, 13% of the whole data set, and the statistical significance. Okay, and we developed the math behind, how to measure the significance in the right way. Okay, and of course we can also see who are the people that are most privileged. So they have the greatest delta in the false negative rate, the people who actually end up committing another crime, even though the predictor said no. And these are, the people who stay in jail less than a week and have no priors. Apparently, they're very likely to commit another crime. Okay, or the white men of actually, I don't know that they were men. The white people over 45 as well. They had these high values of the false negative rate compared to the general population. So the beauty of the tool, in the way we thought it, is that we could just dump data into it, and it would find the subgroups automatically and efficiently. Another thing that we did is this. We wondered, what's the contribution of each item? So suppose that you throw the data into the tool and you are told, okay, these kind of people between 25 and 45, 3 priors, African Americans, males, have a high FPR. And the next obvious question is, well, is it because they're younger, because they're African Americans, because they're male? What's the relative importance of these factors? And so here, this is a bit of a complicated slide, but I didn't have time to do a better animation. So I will talk you through it. This was an old problem studied by Shapley, and Shapley essentially got the Nobel Prize by solving it. Well, he did other work as well, but got the Nobel Prize in economics. So the general problem is this. Suppose I have a team that has a certain value. In this case, the team have these 1, 2, 3, 4 players. Consider them as players in a team. This is the value of the team. How do I attribute the value of the team to the value of the players? And Shapley came up with this way. He considered all the possible orders in which the team could be formed. Did you ever play, I don't know, soccer or baseball? Baseball has different roles, but these games in elementary school, and in Italy, we used to all stand in a line, and then we chose the 2 captains, and then they would choose the players one by one, okay? And so suppose here I choose them in this order. I choose age, prior, race, and sex. Okay, at the end, once I have the team complete, I get 0.22. But if I had only age, how much would I be able to score, right? And so, and if I add prior, how much would I be able to score than if I had only age? So the Shapley value, to explain this formula, the Shapley value is essentially this. It's the average that is the average value that a player brings to the team, averaged over all the permutations in which the players can be added to the team. That is what the Shapley value is. So if you have to form a team of 4 players, there are 4 times 3 times 2 permutations of adding them. Now that's gonna be for 24. Okay. There are 24 ways in which you can form the team of 4 players, picking the first, the second, the third, the fourth. And for each player, you measure what value they give in each of these 24 scenarios when they are added. How many goals the team would be able to score without them and by adding them, and you do the average of that. Okay. And this shapely value has the nice property that is easy to justify mathematically, that if you sum the shapely value of the players, you obtain the value of the team. So it's a real way to divide the value of the team into the value of the players. Okay, and it's very well behaved. And so by using these, we can do the same, considering these as players in a team. We can do these with the attributes. Okay, and for example, in this particular case, in that data set, we see that the biggest factor by far was that they had over 3 priors. This explained over half of the anomalous behavior. And the race and the age was less important, and the sex was actually very unimportant. Okay, so this is very nice because this goes into essentially explainability, right? This was a new insight we had that I think is very powerful when you analyze data in practice, because often you have a concomitance of multiple factors, and this idea of using a shapely value really gave you an easy insight into how to attribute the total effect to the individual components. This is, by the way, a problem on which there is further work to be done. And if any one of you is a math wizard, because true wizardry is needed, this is not one of the many problems in computer science are actually not about writing code. Many problems in computer science are about math. And so if there is any math wizard, let me know, because there are further complications of this problem that will be extremely useful in practice, and very nice work could be done. But it requires people with knowledge of information theory and who find it enjoyable to prove theorems, essentially, okay? And choose axioms, this kind of theoretical work, I guess. So the last question that you may have about this method is this: why is this efficient, right? Why can this be done? If you have m attributes and there are k values per attribute, you have k to the m subgroups. So the number of subgroups is exponential. It blows up very easily. Why can we do this exhaustive analysis of the subgroups that have sufficient representation? And the idea is that we essentially piggyback on results that they had in data mining. Data mining people wanted to find, what are the common purchases in a supermarket. So, the joke about diapers and beer being very commonly associated. So they invented these methods so that when you have a large data set, say, of products that have been bought, you can find the subgroups, in beer and diapers that have high representation. And you can do that efficiently. And the idea is not that you check every subgroup. The idea is that you go repeatedly through the data and essentially increase, while you go through the data, the subgroups that have enough representation. I mean, this is a messy way to explain the algorithm. It just gives you the intuition. The actual algorithm is complicated and was a marvel of algorithmic development. But the general idea was this, that you go through the data and you build the subgroups by traversing the data multiple times. So you never do an exploration of a combinatorial exploration of the subgroups. Okay, so that was the main idea. So what is future work that I'm trying to do here? Anomalies in ranking and in scoring, this has been done. Finding anomalies in unstructured data, there is a lot to be done, and some of it could be done here at UCSC as well. My two Italian collaborators, together with a couple of extra people, we are looking at speech data. That's happening essentially more in Italy than here, because I don't look at speech data very much. So I collaborate with them on the theory. But we have a paper that, I don't know, maybe we'll make it in, etc. But there is more work to be done. But there is a lot more work. For example, what do we do for images? How can we build and explore efficiently subgroups for images in a way that is useful? Okay, so this is fully open for work. Measuring anomalies in selection processes, hiring and admissions. This is work that I'm gonna send in to one day or two, but there is more that needs to be done. Okay. And then also from finding anomalies to curing them. So once you know that you have some subgroups for which the machine learning system doesn't quite work, how do you decide to, how do you go by fixing it, right? And imagine that you got 50,000 data items and you trained your system, and now you know that you don't do well for some part of that data set. How do you decide which data you need to buy, to fix your system at the lowest cost? These are the type of questions. So that's also work in progress. Okay. So lots of work to be done. So the last topic I want to mention is this, just very briefly, machine learning and GPUs for bird habitats and conservation. And this is work joint with Cohen and with other undergraduate students and with Natalia Ocampo-Peñuela, who is a faculty here in environmental sciences. Here we have nothing published, so I'm gonna keep very generic. I tend to keep things a little bit under wraps until we can publish them. But essentially, the problem is this, that for birds, and in fact for many animals, a connected habitat is much better than a fragmented habitat. Because if you have a very fragmented habitat, the birds that are in one of these species, if they by any chance go extinct because, say, a crow preyed on their nest, or because, a storm threw the tree down and the nest was lost. So, I mean, there is a small probability that the population will extinguish in a small habitat, but small but non-zero, and through generations that can sum up. So if you can have a connected habitat that can be repopulated by birds migrating from other nearby places, it's much better than an isolated habitat, which is a sort of, it's a sort of evolutionary trap, because you are there in that isolated habitat, but if you go extinct, you will be extinct forever. Okay, it's like below in Death Valley Junction. I once visited, I think now they don't let people visit anymore, but I've once visited a place that I could find only via GPS, where there is a hole in the ground, where in an area of about 1 meter by 5, it's the only place where a particular species of fish lives. And it's very good for the fish there while they're still alive. But if they ever go extinct, that's going to be it for them, because they cannot be repopulated. There is no other fish that can jump on the desert for, 50 miles to then fall back into that hole. And so the problem that the ecologists have is how do we compute which habitats are connected and how well connected they are? And so ecologists looked at the problem and invented all kinds of marvelous but incredibly inefficient algorithms, because, they are not computer scientists in the end. And when I saw this problem, I thought, well, this is a grid. It's a grid of pixels, that contain bird or terrain or whatever information. And if the grid is homogeneous enough, we should be able to feed it to a GPU, and we should be able to get things done much faster. And so the result, this is one of the outputs of our models. You can see the redder, the more the better connected it is, and then there are islands that you cannot see very well that are less connected, etc. Actually, no, this is the paths that the birds use in order to keep the place connected in this particular image. But so we essentially implemented our work, and this is all I'm going to say about it, because it's still work in progress. So the connectivity depends on the terrain. So we work a lot with the satellite data that is then, analyzed for terrain type. We reduced essentially what used to be a day of computation or half a day of computation to 15 seconds. So the results are incredible from the point of view of efficiency. And what we are still working on is validating the data. We want to show correlations between things we compute and actual bird observations. And so that's what we're working on now. Okay, so that's what I'm currently doing with that group. And so that's it. Those are three things. It's true, I work on quite a few things that are not so related. I think that the real relations are two. One is what brings what I do together is this idea that I want to study these things that interacted with a bit of machine learning or intelligence behind it. And so I'm looking at these various aspects. And the other thing is actually that, you know, I sometimes choose simply because I like working with people. And so the collaboration, for example, on the fairness in AI was motivated by me being a friend of Elena that works in data mining forever, and the two of us discussing over vacation some of the observations that I was having studying the admission process at universities. And so, you know, the work was born out of that. So what's nice in being a faculty is that, you know, you can follow leads and interesting ideas into developing fields. Okay, are there any questions? This is it, basically. Is anybody still here? Yes. Let me stop the share.
I think that is good. I don't think if anyone has any questions, please go ahead and type them in the chat or say them now. But
So to Richard, the answer is yes.
say that again.
No, I was saying to Richard, the answer is yes. He sent me a message on the chat. So
Yes, I'm the one who emailed you, but I'm interested in your research.
yes. So we shall definitely talk. This week is very difficult for me and the next, but then I shall be more things will come down. So we shall talk that Monday.
Okay, I do enjoy the seminar. It's a bit refreshing too.
Thank you. And so yes, I do machine learning without doing machine learning, I guess, is the summary of some of these things, right? So I look at the border of machine learning in many ways.
Do you think you could apply the your habitat fragmentation work to, I guess, ocean like levels?
Could be, but I don't know. To what? To fish habitats or to what?
I guess also like predicting, I guess, like the populations of searches. Yeah, populations. Specifically, I guess, with like increased, you know, carbon in the seas. There's like a certain like light refractive index that might like increase the temperature of the lower water. Or that sort, and then that might drive like some organisms deeper and deeper. So I was just curious, like if your work could be applied to like that sort of thing.
Not directly, perhaps the work, but directly some more general approach that we're doing. That is recently. So in the bird habitat code, some of the things we did is something very cool that I tell you informally here only, but it's called what I call the differentiable algorithms. So in some of the instances, we actually use the real setup of machine learning, which includes gradient descent. In this way, we feed a problem to the GPU, we compute the result out of the GPU, and then we say, hey, propagate the gradient backwards from the result, so that we try to see which places of the input were important. And that's how we got that colored map. Let me share it to you a moment. That's how we got this colored map here. Right? So these colors essentially tell us how much was each pixel important in the health of the territory. Okay? And so this is a very nice, very useful idea. And so this idea, we're pursuing it simply in the for ecology now, for bird habitats. But at the same time, with the Tyler Sorens and another faculty here, Tyler is an expert of GPU programming. And so he started to say, okay, but this type of algorithms generalized in some way is also similar to things that could be useful for other stuff, like weather forecast, or maybe ocean forecast, or other type of simulations. So we are very, very much at the beginning of looking together with Tyler at how to do similar work in more general contexts. But, you know, actual research progresses a little bit slowly. So I think that for the next month, my next, work will be on bird validation. Once that will be, work done, then we will be looking at maybe at more general settings.
That's really interesting. Thank you for sharing.
You see, there is already a lot of work from people that work on weather forecast and on other problems of forecasting on running these things efficiently, right? So I'm not really claiming we innovate on that, but I don't know that all of those people have thought at the concrete capabilities of GPUs already. So this is something that we're interested in exploring. My gut feeling is that there should be a lot of work done, but one is never sure, actually. And again, it's because many of the people, okay, weather forecasting is perhaps an exception, because in weather forecast, there is so much man involved that it would be crazy to learn that they haven't squeezed the GPUs to their full capability. But I do not know the state of it. So it's what you're pointing out is quite interesting, but it's at the margin of what we have been doing.
Oh, there was a question in the chat. I don't know if you want to read it or I can.
What would you recommend is the best way to learn more about ML at UCSC? Take classes by our outstanding ML faculty, I would say. We have a lot of great faculty. You can ask to sit in their ML classes, take them, sit them if they're graduate courses. You may even take some graduate course in AI, maybe they're not so hard if that's your passion, it's not that graduate students are coined out of a different machine than undergraduates, You may quite enjoy sitting as auditor if they let you in a grad level class. So get involved follow courses and if you like a lot what a particular faculty is doing, they ask if they have any project for you. I don't know all the work that is here, but I know that there is incredibly nice work in image recognition, medical applications, fairness in AI. So you look at the faculty we have and I think a few years ago we had fewer people in ML, but now we have quite a few, and I think my suggestion is look at what they are doing. Anything else I can tell you? Okay. Yeah, thank you, Cohen. I don't want to give you names of particular faculty because I don't want my, we hired many of them recently, and so I don't want my advice to be colored by how well I know the people, simply. But I think they're all of them great, actually. So, okay, can I?
I think that's all. If you have any more questions, say so now. But other than that, thank you so much.
Thank you. Thank you, and have a very nice evening.
Thank you.
Thank you. Bye.